So we'll wrap up this chapter dealing with equilibrium. We've covered a lot of chemical equilibrium, and finally we have a little bit of phase equilibrium that we need to deal with. So phase equilibrium. Consider a container. So we may have a vapor over top of a liquid, and it's in equilibrium. So we have equilibrium in two phases present for a pure substance. The book uses a superscript mark like that for one of the phases, and for another phase it'll use two. What are those, apostrophes? Okay. In equilibrium, you do have some liquid that's transforming and going into the vapor phase, but it's balanced by some vapor that strikes the surface of the liquid and gets stuck and now is part of the liquid. So you have molecular exchange going back and forth between the two phases. In equilibrium, we've been accustomed to this Gibbs function, and we set the change in the Gibbs function equal to 0. Without any, I know the textbook spends a number of lines and maybe a couple pages on this derivation, but basically they say that you have a molar Gibbs function for that phase, let's say the vapor phase, multiplied by the change in the amount of the vapor phase. That's a change in the number of moles that are in the vapor phase. That could go up or down. We're going to derive this equilibrium condition, but it's an exchange, plus the molar Gibbs function in the other phase, here I say that's liquid for an example, times the change in the amount in the liquid phase. So this G bar for each phase is the molar Gibbs function. It's also sometimes called mu. That's somewhat confusing, but mu is the chemical potential. What units does mu have? What units does the molar Gibbs function have? Well, it would be something like kilojoules per kilomole. Again, what do those primes indicate? They indicate the phase, 1 and 2 used by the textbook. So at equilibrium, this the change in the Gibbs function for a fixed given temperature and pressure must equal to 0. And then we look up here and we see that you have G bar prime minus G bar double prime times dN prime is equal to 0. Why? Because dN prime is related to dN double prime. Okay, the change in the amount of the vapor is related to the change in the amount in the liquid, because if one's going up, the other's going down, the total N is conserved. So there's the relationship. And you use that to reduce from here to there. And so what you're finally left with for equilibrium is that the molar Gibbs functions are equal for the two phases. The molar Gibbs function in the liquid phase is equal to the molar Gibbs function in the vapor phase. Or another way of saying it, the chemical potential in the vapor is equal to the chemical potential in the liquid. The two-phase chemical potentials are equal. Let's apply this concept. The property data from the steam tables show that the specific Gibbs function, that's at G bar, of saturated liquid, okay, liquid, double prime is our notation for liquid, and saturated vapor, that's G bar prime, for the vapor, are equal for steam at 150 degrees C. Is that equal? You want to show it. So we want to calculate G bar double prime. That was for the liquid, right? Well, what is the definition of G bar? It's going to be H bar minus T S bar. True? And if this double prime is for the liquid, and we're talking saturated liquid, that H is H of F and S of F. Make sense? Okay. The other thing is if I take both of these equations here, I know it's written on a mass basis. Can I express it like this? G bar, G double prime equal to G prime. Can I express it on a mass basis? By taking and dividing both sides of the equation by the molar mass. Will that work? So I don't really want to do it on a molar basis because my steam tables are all on a mass basis, aren't they? So we'll go ahead and substitute numbers. So for H of F, we find it's 63.2.20 minus the temperature of 150 degrees C, convert that over 423 Kelvin, times S of F, 1.8418. I left the units off, but when you make the math calculations, it's negative 147 kilojoules per kilogram. That's the Gibbs function, the specific Gibbs function in the liquid. You do the same thing for the vapor. That's H of G minus T S of G. Substitute numbers. It's 27,406.5. No, 2,746.5 minus 423 times 6.8379. And you get that it's negative 147 kilojoules per kilogram. They agree to 3 significant digits, and you could get more if you were in a computer code, but this is good, the 3 significant digits. So we just confirm that G prime is equal to G double prime. What happens if you have a multi-component mixture that has at least 2 phases? So think about having a container that has a vapor in the presence of gravity on top of a liquid, and there's a mixture of component A and component B. Some of it's in the vapor state, and then there's also some in the liquid state. At equilibrium, what's happening, there's some A going from liquid to vapor and some A going from vapor to liquid. Likewise, there's some B going from liquid to vapor and some B going from vapor to liquid, but at equilibrium, those rates of exchange are balanced. So we have still 2 phases. We'll use the prime, double prime for the vapor, and then the liquid. And then for the equilibrium, what you want is that you want the change in that Gibbs function for the vapor phase at some fixed temperature and pressure to be equal to 0. And you also want the change in the Gibbs function at a fixed temperature and pressure to be equal to 0 for the liquid phase, the other phase. Well, that's equal to the chemical potential. I know this textbook now switches to chemical potential at this point instead of the Gibbs function, times the change in the amount of A in that phase plus the chemical potential of the species B, or component B, the change in the amount of B in that phase. Likewise, mu of A double prime dNA double prime plus mu of B double prime, I left the prime off here, times d sub n sub B double prime. And the 2 phases aren't independent, so that you have, if you're changing the amount of A in one phase, it's equal and opposite the amount of A, in the other phase. Likewise for B. And so lo and behold, you substitute those in, you find 2 constraints. One is the chemical potential for component A, and let's say the vapor phase is equal to the chemical potential of component A in the liquid phase at equilibrium. Likewise, the chemical potential of species B is equal regardless of what phase it's in. Phase, first or second phase. So at equilibrium, that's true. One of the last topics I need to cover is the Gibbs phase rule. right here, Gibbs phase rule. And to cover the Gibbs phase rule, go back and think about Chapter 1 or Chapter 2. There was a state principle in thermodynamics. What did it say? It said that for the types of systems that we study, pure systems, so think of a pure substance like water or pure refrigerant, okay? And it's a simple compressible system, meaning that you can change its volume, you can have some work out, you can have some heat transfer in and out. That two independent intensive thermodynamic properties are required to fix the state of the system. And once you fix the state of the system, you can, in theory, evaluate all other intensive thermodynamic properties. And we had a whole list of properties, didn't we? We started with maybe pressure, temperature, specific volume, internal energy, U, then we had H and S, and then we had X or G, and you even have Gibbs function, you have Helmholtz function, you could even throw in specific heats, you just have a whole pile of them. But for the types of systems that we've been studying, typically temperature and pressure, those are the two we like to have as independent. And then we go and evaluate all these others. But every now and then we have to evaluate H as a function of pressure and entropy, as long as pressure and entropy are independent. That's the state principle. Well, now that we have multi-component systems with multi-phases, we generalize that concept with the Gibbs phase rule. So here's the bottom line for Gibbs phase rule. F, the number of degrees of freedom needed to fix the state, is equal to 2 plus n minus p. Well, it looks like the state principle. You need two independent intensive properties, but it also depends on n. N is the number of components. So what could be in a component? An example of a component would be water. What's another one? Maybe one of the refrigerants, ammonia, NH3. Maybe another one, I don't know. You could put in something else that I don't want to put in. Well, I'll put in something that is, let's say, CH4, ... Something that's not necessarily behaves as an ideal gas. If I put in oxygen and nitrogen, you think, oh, he's putting in ideal gases. But I want to put in something that doesn't necessarily have to be an ideal gas. But those are the number of the components. And then P. Guess what P stands for? The number of phases. So P can be, could it be 0? No. Could it be 1 if it's pure liquid, pure vapor, pure solid? Sure. Could it be 2? Oh, a liquid vapor combination, a solid vapor combination. You know what I mean? Could it be 3? So P goes between 1, 2, and 3. That's what it does. For this class, I know if you go to the materials class, you can find Gibbs phase rule, and they'll have different phases for your solids. You could have more than 3. You have this phase, that phase, this phase. Okay? But for this class, the phase is either liquid, vapor, solid. 1, 2, or 3. Okay. How did they come up with this? Well, they said, okay, the quick derivation is we'll have all our systems are simple compressible systems, so we have the temperature and pressure. We just threw you the curveball of having multi-components. So if you think about the multi-components, you have the multi-components you describe by mole fractions. Why? So you would have the mole fraction of H2O, the mole fraction of NH3, the mole fraction of CH4. Let's say CH4. If I only had those 3 in there, only 3 components, if I sum those all up, what does that have to equal to? 1. So what you have is you have the y's go from 1 ... up to n. That's how many mole fractions you have, because there's n components. But you have 1 minus, or n minus 1, independent Y's, or independent mole fractions. All right? And now, if you multiply that by P, you would need the mole fractions of n-1 components in 1P, 2P, or 3P for each of the phases. I need to describe it in the, if I have liquid vapor, I need, P will be 2. I need to have that many descriptions. Okay? All right. And so you have the 2 for the temperature and pressure. You have the number of mole fractions minus 1 times P is the total number of independent Y's. P, all right. And then you also have the number of equilibrium conditions. What are the number of equilibrium conditions that are inherent in these multi-component systems? Well, I'm going to have to go back here and use this little bit of room up here. Is that we had that the mu for species A in this phase was equal to mu's of A in this phase. Excuse me. That was for 2-phase, P is equal to 2, and if you had P equal to 3, mu's of A in that phase, so P equal to 3, right? Well, if I have P equal to 3, how many equations do I have for component A? Just 2 equations, right? So what you have is you're going to have how many of these? N components, so you subtract off N times P minus 1, which is the number of constraints at equilibrium from the chemical potentials. So you do the algebra and you're left with F is equal to 2 plus N minus P. That is the result. Look good? Very simple for this class. It's more complex when you have lots of different phases of solids in materials. How many independent intensive properties F are required to calculate the specific enthalpy of pure water in the liquid phase? So this is an application of Gibbs' rule. So we recall the equation. What was the equation? F equal to 2 plus N minus P. So for this problem, what is N? It's 1 because it's pure water. And what is P? 1. There's only one phase, it's liquid. And so F is equal to 2, so we're back to where we started from. If we wanted to find the enthalpy, I need 2 independent intensive properties, maybe temperature and pressure. Or maybe temperature and pressure aren't independent. Maybe it's temperature and quality. Or maybe it's pressure and entropy, whatever. But I have to have 2 independent intensive properties to fix the state. Let's apply it to another problem. How many intensive properties F are required to calculate something like the specific enthalpy of a liquid solution of water and ammonia? So F is equal to 2 plus N minus P. What would be N in this problem? N is 2 because you have water and ammonia. And what is P? 1. So what is F? 3. So what's an example? Well, if I have this water ammonia mixture, it's a liquid state, and I wanted to find the enthalpy, it's more than just temperature and pressure. I need some other information. What's that other information? Mole fraction. Could be the mole fraction of water. Or it could be the mole fraction of ammonia. You say, what's the difference? One minus the other is the other. Okay? Because the sum of them have to equal 1. It could be something like temperature, entropy, comma, mole fraction of H2O. Whatever the two independent, plus I need another property, which is the mole fraction, or most logically the mole fractions. How many independent intensive properties F exist for a pure substance in an equilibrium solution? All of these solutions are in equilibrium with the solid, liquid, and vapor phases present. And I'm going to pause and I'm going to see you work this one out. So I just want to calculate F is equal to 2 plus N minus P. And I'll give you just a minute to do it. All right, so what do we have? We have 2 plus the number of components 1 minus the number of phases 3. This is equal to 0. So if I said, go get me the enthalpy of what substance? It's a pure substance. Let's say the pure substance is H2O. In an equilibrium solution of solid, liquid, or vapor, really what I'm saying is you're going to have the enthalpy of the S, the enthalpy of F, and the enthalpy of G. That's the enthalpy of each of those independent phases. But they're not a function of anything because there's 0 degrees of freedom. These are just numbers that are reported typically in tables. What point is this where you have solid, liquid, and vapor of a pure substance all in equilibrium? It's the triple point. And so you could go look up those values of H for each of those phases. Now, that's intensive properties. If you wanted the extensive property, or you have to know how much is in each of the phases. But there's an application of the Gibbs phase rule.